Bismillahirrahmanirrahim. Assalamu alaikum. Our today's topic is about transition elements. Now, the properties of transition elements. They have large charge over radius ratio. They are hard and have high densities. They have high melting and boiling points. They form compounds which are often paramagnetic. They show variable oxidation states. They form colored ions and compounds. They form compounds with profound catalytic activity. Elements in the periodic table, the D block elements, are called transition elements because they exhibit transitional behavior between S block and P block elements. Their properties are transitional between highly reactive metallic elements of S block, which are ionic in nature, and the elements of P block, which are covalent in nature. Likewise, we can say that the D block elements construct a bridge between the S and P block elements. It is important to note that zinc, cadmium, and mercury are not considered as the transition metals as they consist of fully filled electrons in its d orbital. Transition metals are small in size and have positive charge density ions. Now it is S block element 1A and 2A. It is P block element 3A, 4A, 5A, 6A, 7A and 8A. Transition metals, that is D block elements, are present between S and P block elements. It is 3B, 4B, 5B, 6B, 7B, 8B, then 1B and 2B. And at the bottom, these are F block elements. The D block elements are called transition elements. The main group elements are actually in two groups, the S block and the P block. These S block elements and P block elements, these two are the main groups of periodic table. These two, let's call them subgroups, are separated in the periodic table by a special group of highly colorful compounds known as transition metals. The transition metals represent groups 1B through 8B of the diagram. That is 1B through 8B. And they are formed as electrons are filling in the d orbital. This is why they are referred to as the d block. We will look at all of this in this lesson that follows. Now the elements of the transition metals. These are the elements, their electronic configuration represented by Z, noble gas configuration, and electrons in box diagram for 4s and 3d. It is 4s and these are 3d. Number 1 is scandium. Its Z, that is atomic number, is 21, and it is the electronic configuration of scandium. And the noble gas electronic configuration, that is argon, is 3d1 and 4s2. Now it is the electrons of scandium, that is 4s2 and 3d1. Now the second is titanium, atomic number 22, and it is the electronic configuration of titanium, and is the electron in box of titanium, that is 4s2 and 3d2. The third is vanadium, atomic number 23, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3 and 4s2. 4s2 and 3d3. Now chromium, electronic configuration, atomic number 24, and it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. It should be 4s2 and 3d4, but according to rules, the half-filled orbital is more stable than full-filled. So, if electron goes on 4s2 and 3d4, it is unstable, and if electronic configuration is 4s1 and 3d5, it is more stable. Now manganese, atomic number 25, and it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s2. That is 4s2 and 3d5. Iron, atomic number 26, it is its electronic configuration 4s2 and 3d6. Cobalt, atomic number 27, 1s2, 2s2, 2p6, 3s2, 3p6, 3d7 and 4s2. 4s2 and 3d7. 1, 2, 3, 4, 5, 6 and 7. Now nickel, atomic number 28, and its electronic configuration 4s2 and 3d8. Now copper, 4s1 and 3d10, that is electronic configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s1. Electron goes first in 3d10 because full-filled, half-filled S and full-filled D in case of copper. Now zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2. 4s2 and 4s in case of zinc. The electronic configuration is 4s2 and 3d10. So it is fully filled d orbital. Because of it, the valency of zinc is 2. Zinc does not show variable valency, and it shows positive. It makes positive 2 ions after the removal of 4s electron, after the removal of 2 electrons from 4s2. Now electronic configuration of ions, 4s filled before 3d, so 4s lost before 3d, first in, first out. Scandium positive 3, titanium positive 2, ferric positive 3, copper positive 2 and zinc positive 2. These are the electronic configuration of their ions. They form colored compounds. FeH2O6, that is, it is green in color, and FeH2O6 positive 3, it is ferrous and it is ferric, it forms yellow colored hydrate, that is ferrous hexahydrate, and it is ferric hexahydrate. Now copper, CuH2O6 positive 2, and CuCl4 minus 2. It is copper chloride, Cr2O7 minus 2, chromate, and CrH2O6 positive 3. It is purple in color. Now manganese, MnH2O6 positive 2 ions, and MnO4, this permanganate, which is purple in color. Catalytic activity, heterogeneous catalysts and reactants in different physical state. Uh, in Haber process, iron is used as a catalyst. In contact process, vanadium pentoxide is used as a catalyst. In hydrogenation of alkenes, nickel is used as a catalyst. And decomposition of hydrogen peroxide, manganese dioxide is used as a catalyst. Homogeneous catalytic and reactants is same physical state, iodide plus peroxodisulfate catalyzed by Fe positive 2 or Fe positive 3, that is iron 2 or iron 3, S2O8 minus 2 plus 2 Fe positive 2, SO4 minus 2 plus Fe positive 3. In this reactions, adsorption take place. Ferric, iron, vanadium pentoxide, nickel and manganese adsorb hydrogen. Now Fe positive 3 in this homogeneous catalytic reactant is same. Fe using its ability to change oxidation state to catalyze reaction. Iodide plus peroxodisulfate catalyzed by Fe positive 2 and Fe positive 2 change into Fe positive 3 because transition metals show variable valency, and now Fe positive 3 react with iodine. Iodine is formed, and then Fe positive 3 takes electron from iodine. It gains electron from iodine. Now S2O8 2 minus plus 2 Fe positive 2 plus 2 Fe positive 3 plus 2 iodide. It is the complete reaction. And finally S2O8 2 minus plus 2 iodide forms sulfate and iodine. Now thank you very much. Allah Hafiz.